All right. So let's look at today's lecture, the second lecture for the semester. I think as a recap to last week's class, we had or we discussed what's or we recapped an previous course, CENG 155. So we looked at what loads are, and then went through the various support conditions. And then from there, we looked at how to analyze um, a typical beam. And also, so by analysis, we're looking at its external reactions and also the internal behavior, where we ended up with calculating for the shear force and the bending moment. All right, so I think um, going back, we solved how many questions? Two questions. Okay, so we were able to um, at least go through two examples, which I think should be okay to um, help us to remember what we did in the previous academic year. Okay. So let's start with something new this morning. Um, all right, so then let's start with the subtitle, deflections. Okay. So let's look at typical beam. All right, let's say a beam in a building so that I can explain the concept of deflections to us. And then we can look at what they are. All right. So if you have a building, so let's say a house. All right. Okay. So maybe let's look at this critical beam over here. Definitely, if there are people, let's say it's a residential facility. So there are people who use this particular building and then they go up and down or go in and out. The people here act as what load on the beam. All right. So if I'm to draw it in simple terms, we would have these loads on it. Okay. What happens is that with time, because of the presence of the load, with time, your beam will begin to bend. Okay. So the beam that was initially assuming as reinforced concrete beam, the beam that was initially cast as straight, over time begin to undergo some form of bending. All right. And which means that, so let me exaggerate a little bit. Let me make this one thicker. Okay. So that if it bends, I'm just exaggerating the bending. It doesn't bend as much, but to illustrate what goes into structures. So here, if this point was point C, all right, which means that after a while or after some time, your point C has now moved to this new position. Let me call it C prime. All right. So it means that your point C has changed location vertically. All right. So because it has changed location vertically, it means that we can calculate. So if there's the initial position, let's say maybe at time t equals 0. Now this is your current position. At some time t equals maybe t1, maybe 5 days, a week, maybe a month after construction or moving into the structure. This becomes your beam now. All right. So it means that the beam has undergone some form of deflection. Okay. And this deflection is critical to us as engineers in the sense that Um, when we're defining what a structure is, one of the key things that we mentioned was that a structure should not deform excessively. Okay. So I think the key word here has to do with excessively, which means that there would be some deformation occurring, right? It doesn't matter what structure we have, it would, no matter how well they are designed, how well they are constructed, they will deform, right? But then the key thing is that we don't want them to over deform. Okay. So any beam that we have in any of the classrooms or campus, they have some form of deformation or some form of bending has occurred within the beams. Okay. Now, as to how much deformation can be allowed or how much deformation should occur before we say that the deformation is excessive, all right, is what we engineers think about or we work with. Okay. Um, so if the movement of the structure or if the deformation of the structure, so if the deformation typically um, if the deformation affects the use and the suitability let's write the whole thing. So if the deformation affects the use and suitability of the structure for its application, then it means that that structure is unsafe, right? So the structure is unsafe. Okay. So let me put the unsafe in quotes because sometimes the structure can still be safe, but because the deformation is excessive, it creates the perception that the building could collapse at any time. So no one would want to be in that particular structure. All right. So what we do in engineering or in design is that we try to minimize the deformations. Right. So one of the key things in design is that you look at what we call serviceability loads. You look at them in third year. Serviceability loads are loads that we take into consideration when we are thinking of deformations. Right. We don't want the building or the beams or the columns or the slabs to deform beyond a certain value. Right. So most of the codes which are used to design these structures, whether it's the EC2, the European Code 2, whether it's the BS 8110 or the BS 5950 or the EC3 or the EC5, all of them have um, guidelines as to how much deformation is allowed, or they put a limit to how much deformation you should allow within your structure so that once your deformation exceed the limit specified in these codes of design or these standards, then it means that we can term your deformation to be excessive, which then makes the building unsafe for its intended use. All right. So in as much as we are looking at shear force, we are looking at bending moment, we are looking at axial force, they are to look at the overall stability of the structure. So can it support the load? Can it transfer the load? That's generally what these shear force, axial force, and bending moment considerations are. But there are other considerations that we look at when it comes to design. And one of them is deflection. How far the beam bends. If it's a column, how far the column buckles. All right. So for example, for the column, if this is my column, okay, so this is a column, depending on what load you have on the column can actually behave like this. Okay, so it begins to bend, so it can buckle, it can also crash, right? And sometimes the buckling will cause some bit of horizontal deformations, and all of these need to be taken into account. All right. So as part of this semester's course outline, we need to study or we need to come up with how to calculate deformations. All right. So we know how to calculate shear force, bending moment, and axial force. So those are the internal forces. We also need to calculate the deflections that do occur in the structure so that you can compare these deflections that will occur, delta, with the limit which is provided in the design standard. Okay. So as I mentioned, some of the design standards are the BS, BS 8110. So there's a British standard. There are so many of them. There is the BS 5950. So this deals with concrete, anything concrete. This deals with anything steel. And I think there's one for timber. I think that's a BS 5860. Don't take my word for it. That's 60 or 30. I've forgotten the code, but that deals with timber. Okay. And you also have a similar one also in the Euro code. I think, yeah. I could be, this is correct, this is correct. I'm not too sure of this one. So these are the different standards, and they would provide you with the limits of deflection that you should have. All right. So what it means is that when you calculate your deflections in the beams, they should not exceed the limits provided in these design standards, okay, or code as we call them sometimes. Okay. Yeah. So usually when you have excessive deformation, the building becomes or the building is perceived by the occupants as being unsafe or uncomfortable, right? For example, if you had come into the computer lab and you've seen that what's the name? You've seen that the beams are like visibly deformed, your mind will tell you that this is not a safe building. Okay. If you go to the other room, the room I think after the lab that they share the same partition, you see that when you go there, even with the computer lab, some of the tiles are removing. Okay. When you go to the next room, you see that the tiles are budged up. All right. And once you enter, there's a sense of the place being unsafe. All right. Structurally, the building is fine, but the fact that certain components of the building are deforming or behaving in the way that is not acceptable, it creates the impression that the building is unsafe. All right. So what causes deflections? All right, we just look at some of them. What causes of deflection? One of the obvious reasons has to do with the loads. Right? So the loads can be any of the loads. It can even be the self weight of the structure. So the loads can be, let me just put it over here. It can be the self-weight of the structure. Okay. So you don't necessarily have to have the occupants in there. Even buildings that do not, what's the name? That do not have any occupants, but they're just there, their own self-weight can cause deflections to occur. or some form of deformation. Okay. Then it could be the live loads and pretty much any form of load. Wind loads, earthquake loads, earth loads, snow loads, hydrostatic loads, they can all um, cause some form of deflection within the structure. Then the next one would be temperature changes. And this one is more susceptible to steel structures. All right. Because they tend to respond more to heat than concrete. So where there's a fluctuation in the temperature, mostly between day and then day and night or day and morning, you realize that when for steel structures or for any material made from iron, you would realize that it expands when the weather is hot, and then it contracts when the weather is cold or when the temperature has dropped. There are certain materials which act differently. I think one of them is aramid um, materials. They they expand when the weather is cold or when the temperature has dropped, and then they contract when it's increasing temperature. So, for example, if you have um, a beam, a steel beam, which has fixed support at both ends. All right. So it means that, let's say at time t equals 0, maybe the temperature there, um, temperature is equal to 0 degrees. Let's work, or let me say maybe 25 degrees Celsius. So that's your temperature. So everything is straight. There's not really any expansion. Then when the time moves to maybe, let's say, during the day or some other time, you'll realize that the temperature has now increased to maybe, let's say, I'm exaggerating it, it's about 40 degrees Celsius. Okay. So at 40 degrees Celsius, the steel member is supposed to expand, but because of the presence of these fixed supports, it will not allow any expansion to occur. All right. So sometimes it means that stresses will be built up within the steel member, and this could cause it to deflect downwards. Let me draw it properly. Okay. So there can be some deflection occurring due to the fact that there's been increase or decrease in the temperature. Okay. The other one to be fabrication error. Okay, and this usually happens during the manufacturing process of the steel member. All right, so during manufacturing and also during welding, especially if you are joining different members together. So this can happen during manufacturing. And then during welding. Okay. So again, this will be pretty much common to steel members, where fabrication errors can lead to um, maybe a longer than usual length. Maybe, for example, if you have, again, I'm still using the beam. Maybe on paper, the length of the beam should be less about, maybe let's say 5,000 millimeters. So that's what it's supposed to be to fit within a certain, to fit within part of the structure. All right. But then maybe during the fabrication process, the length was unfortunately maybe increased to maybe there was an extra 10 millimeters added to it. So when you're trying to fix this into the building during the assembly process, you'll be forced to fit the 510 mm beam into a space of 5,000 mm. So it means that that extra 10 would have to be pushed somewhere, and this could cause the beam over time to also deflect to accommodate the smaller space it finds itself in. All right. So all of these are taken into consideration. Then we also have settlement. Settlement of the structure. Um, Settlement comes into play when we are looking at buildings in relation to the soil. So again, if you have let me draw this nice building, which is corresponding. Oops, the footing should all be on the same level. Let me just make sure they're on the same level. Okay. So I'm guessing we all know what footings are. If not, we'll look at them maybe going forward. So the foundation, right? So this is the foundation. So let's say this building, a portion of it, I want this beam. So let me put this beam over here. Okay. So this footing, let's say the one on the right, it sits on a rock or a rocky material, and then the one on the left maybe sits on clay or maybe silt, something that can easily be displaced. All right, actually, if it's wet. So let's say you put this building up in the dry season. So in the dry season, the clay is hard, behaving as though it's rock. So they both are on the same level. All right. Then comes the rain. All right, where comes the wet season where the water table in the soil goes up. So then that begins to affect the clay, which means it's easier for the left footing to displace downwards. Okay, so it moves downwards. Okay, so once this moves downwards, it means that your building on the left would also be forced to move downwards, while the building on the right stays upright because it is on a rock. So there isn't going to be any much displacement or movement downwards, which will then force the beam, which was initially straight, to now more or less bend downwards, right? So it means that with respect to its initial position, there has been some deflection occurring. Okay. And again, in buildings, we want to avoid this as much as possible, right? It's either you have uniform settlements or you prevent differential settlements, right? So when the settlement of the structure happens in the sense that one area deflects more than the other, that is differential settlement, and we try to prevent that from structures because otherwise this can easily cause cracks in the buildings, and then over time it will lead to overall failure of the structure. Okay. So in all these cases, one of the common effects of deflection will be crack formation. Okay. So these are like some of the effects of the formation. So that'll be crack formation. And then obviously also affecting the structural integrity, right? So affects So I think there are some buildings. I remember this particular building in Kumasi. I want to remember the localities found. It's around KNUST. Um, it's a very tall structure, and for many years it has been unoccupied, and the reason is because the perception was created that the building was sinking, right, or it was undergoing differential settlements, right. So because of that, the owner of the building could not sell the building out because nobody wanted to come in and then stay in that structure. And it's not just that building. There are quite a number of them across town, both in Accra, where they have stayed empty because of the fact that some deflections had occurred, and then overall, I mean, human perception makes it impossible to sell the structure. I think a few weeks ago, was it? Yeah, I think a few weeks ago, there was this video that was circulating where a residential building just collapsed on its own. Um, and I think it was shared across the social media platforms. All right. One of the likely causes of such deflections could be the fact that there was differential settlement. All right. Because it didn't look as though it was a failure of the structural members because the building just went down straight. So if it was a failure of the structural members, it would have either gone sideways or so, but this went down vertically. And one of the major causes of that could be the differential settlement of the structure. Um, all right. Mm. So with the deflections, they can be vertical and they can also be lateral. All right. So far, what the examples we've been looking at are vertical, where it deflects downwards. This is an example of a lateral deflection. Lateral. Let me write it well. LATE. Let's see where it's done before. So lateral deflection has to do with horizontal deflection, deflections along the x-axis, right? They do also happen, and these can be caused by loads like wind loads, because they are also horizontal loads. It can also be caused by earthquake loads. It can also be caused by earth, and then I think hydrostatic loads, because they are typically horizontal loads. Okay. So before we go into calculating anything deformation, normally when we are looking at deformation, we do what you call the elastic region. I'll explain what that is. Okay. Now, when you apply a load P, so let's say at its initial position, no load has been applied to the structure, so the structure remains as it is. There is no deformation of that structure. But then when we apply a load P to the structure, over time, it takes this deflected shape, okay, due to the load. Now, when we take the load away, so when load is removed, the expectation is that the beam should return to its initial position. Okay, so that's the idea. So anytime you apply a load to a structure and then you take away the load, whatever deformation that has been caused in the structure, that information should ease away so that it goes back to zero. All right. when that happens, we say we are within the elastic range or the elastic limits. The elastic region or limits is a region whereby any deformation is not permanent. Okay. So I think last semester when we were looking at engineering materials, where we're looking at I think the stress strain curve for I think for steel or so, where we mentioned that if this is your strain, this is your stress, your plots could go, so you could have some linear variation, have a curve, go all the way up, and have something like this. All right. So this region here is what we call the elastic region, where deformation is recoverable. Okay. So deformation is recoverable, right? In the sense that once the object that is causing the deformation is taken away, your structure comes back to zero. So here, deformation is not permanent. Okay. So most structural design are based on this concept that deformation is not permanent. Typical structural design are based on that. All right. So we typically look at the linear, what you call the linear elastic material response. Okay. And that's um, the straight line portion of your plot, where only the or where the formation is recoverable. All right. So let me not spend too much on that. And that's what pretty much governs all our analysis in this case. I mean, for this for your 4 years, all our structural analysis is based on the fact that we are looking at the linear elastic material response. At higher education level, you might start looking at the plastic response, but for now, almost everything that we are doing is in the linear elastic response. Um, okay, so I think let me see if I have to add something before I move to the next item. So pretty much when you have the beam and then you have some deflection ongoing, I usually draw a simply supported beam for this. Okay. So this deflection that is ongoing in this beam, that deflection can be akin to what you call the elastic curve. Okay. The elastic curve is just a curve which depicts, so this depicts, is that how it's called depicts? I think so. So this depicts um the deformation. Okay. Okay. So this depicts the deformation. So that's the idea of the elastic curve. And or should I say this also depicts the deflected shape? Okay, maybe let me put the word deflected shape in the bracket. So this also helps with the deflected shape. Okay. So naturally, we should be able to know how to draw the deflected shape. Okay. There are a few things I have to mention. So the deformation, as we know it, okay. Or let me make the deflections rather. Okay. The deflection, as we know it, can be broken down into two subcomponents. For clarity's sake, you can have displacement. Then we can also have rotations. or slopes. So let's use delta to represent the formation, and then use theta to represent the slope. Okay, I would explain what a slope is shortly. So at least if this is your point C, or if this is your point C, it has now moved to somewhere here. So there's displacement. C has displaced vertically downwards. Okay. When a beam also deflects, let's call this point maybe B. So this is B. Okay. So when B also deflects, so let's say the deflection of C is delta C, the deflection of B is also delta B. At the same point, because of the fact that it's a curve which is occurring, there will also be a rotation. Okay, let me draw this with a different color. So there will be a rotation, all right. And this rotation is the angle, the tangent. So this is a tangent at B. So this is B at its current position. So the tangent at B, the angle that tangent makes with the horizontal becomes the slope. Okay. So in effect, if I draw the same tangent here just to expand on it, so this is tangent B. Sometimes the screen acts up, and it's one of those. Okay, so it's back. So this is tangent B, and here is point B. Okay, so the angle it makes with the horizontal, this angle here, is called theta B, and that's the slope. Okay, so anytime a beam is deflecting, there are some point along the beam that would also undergo rotation. So whilst it's deflecting, it's also rotating, right? And all these two are looked at so that it doesn't affect the behavior of the structure, both short term and long term. Okay. So how do we calculate this displacement? How do you calculate all of these rotations and all of that? All right. To do that, we have a few terms that we look at. So we have to look at what we call the Bernoulli um, Euler beam theory. I'm pretty sure you guys have heard about Bernoulli from your fluid mechanics class. Then we can look at, so based on that theorem, we can develop other terms. So to the Euler, the Bernoulli Euler beam theory is what is used to help us to develop other methods that can be used to calculate what's the name? Calculate deflections. All right. So with that, we have what you call the double integration method. Integration method. We have the moment area method. Then we have the conjugate beam method. Okay. So these two, the moment area method and the conjugate beam method are what we call the geometric methods. Okay. We would understand why we call them the geometric methods very soon. Okay. So this is the method by which we use to calculate deflections. All right. Typically, these methods are used for um, statically determinate beams, right? So we are still within the statically determinate environment. We've not moved to the indeterminate environment yet. All right. So these are basically these methods. We'll try and do some of them today. Um, so let's look at uh, let me structure this well. So now let's look at the supports, general supports, and how supports behave in terms of deflections. Okay. So let's say supports. No, this is not the right color to use. So in this case, we are looking at supports in terms of displacement and in terms of what's the name, rotations. All right. So let's say I have this. This is too much. So we know this support as a pin support. Pin or pinned. I mean, it goes back to the same thing. So when you have a pin support, what happens is that this is typically how the deflected shape, a portion of it looks like. I think, let me draw it well. Okay, so it has this curve, elastic curve to it. Okay. Now, when you take, let me call this point A. Now, when you take point A, um, we know that this point or the support has how many reactions? It has two, right? HA and VA. Okay. What reactions mean is that they are resistance to certain movements. Okay. There are typically three types of movements that we look at. So three main movements, okay, at every support. So we have the vertical translation, the horizontal translation, and then rotation, which we call moments. They also have rotations. Okay. So rotations about a point. Now, if you look at a pin support or a hinge support, because a hinge support has reactions, it has these two reactions, it means that it prevents what's the name? It prevents translation. All right. And translation is simply what it could be a right and left movement or an up and down movement. Okay. So here what it simply means is that once there are these reactions, it means that the that deflection at A will be zero because your reactions HA and H and VA will prevent any form of movement. All right. But when we come to the slope, because a pin support has no resistance against rotation. All right. And that's how come the moment at A0, the moment at A0 because there's no resistance against rotation. The way you can picture this is to look at the door hinge or anything that has a hinge, right? Once it has a hinge, it can rotate about a point. So the reason our doors or gates can move is because they are moving with respect to a fixed point, and that is the hinge. So they are rotating with respect to the hinge. our doors cannot move up and down. And you can also pull the door towards you horizontally, right? Because of the whole hinge support effect, right? So because it so because it has no resistance against rotation, then it means that the rotation value at A will not be zero. Okay. So that's how we're able to determine what would happen at a support. So if the rotation at that point is not zero, then it means that I can take a ruler and then draw a slope so that this angle here becomes my theta A. So I'm drawing a tangent from A. So I call this one tangent A, or the tangent at A, right? And the angle it makes with respect to the horizontal becomes my slope. Okay. Now let's look at the other supports, the ruler. Ruler support, which behaves pretty much the same way as that of the pin support. So again, we have that. Okay. And then in terms of its reactions, it has one vertical reaction. Oops. VA, which means that if you're looking at the vertical displacement, that means that very similar to what we have for the similar to what we have for the pin support. It means that our displacement at A is 0. And again, it has no resistance to rotation. So our rotational slope at A would not be 0. Okay, so this for the ruler support. And then we can also apply the same idea to the fixed support. Okay. So let's look at the fixed supports. If at some point you don't understand what is happening, you can always alert me and then I can go over it. Okay. So for a fixed support, this is what we have. So this end is fixed, and this is how we draw a fixed support. Okay. In terms of its reactions, a fixed support has how many reactions? It has a VA, it has an HA, and also has an MA. All right. So it means that for a fixed support, it has three reactions. Okay. So if it has three reactions, it means that if I'm looking at, so this point is A. If I'm looking at the rotation at A, sorry, the displacement at A, because there's resistance VA and HA, the displacement at A will be 0. Now the rotation at A would also be 0 because there is a moment reaction. All right. A reaction simply means preventing motion. All right. In the simplest terms, you are preventing motion. All right. So once a support has some reaction to a certain direction, then it means that it is preventing motion or movement in that direction. Okay. So a fixed support has rotation reaction, which is the moment, or a rotational reaction. So by implication, it means that it is preventing any form of rotation. Okay. So normally this is how you would draw. So from A, it maintains some form of like a straight line for some distance before the bending occurs, right? Because at A, there's no rotation. Okay. So A is a fixed end, B is a free end. So B is a free end. So B is a free end. Okay. And A is a fixed end. We are focusing on A for now. Okay. Then the next thing to look at, the other support condition that we can look at is the free end. So with a free end now, our focus is on B, not on A anymore, right? So coming back, I can draw Let me just draw this here. Okay. So the focus here is on B, the free end. Okay. At the free end, there's no reaction. All right. So because there's no reaction, so your your HB, your VB, your MB, all of these will be zero. Okay, so there's no reactions at B because there are no supports to provide those reactions. What this means is when I draw my elastic curve at B, now this is a new position of B, okay, which means that there will be some deflection occurring, delta B, and again we would have some rotation also occurring at B. Okay. So then the angle this makes with the horizontal here will be theta B. All right, because there's no moments, there's no what's the name? There's no vertical or horizontal reaction. Okay. And if this is the initial position of B, which is here, oops. If this is the initial position of B, and now this is the new position of B, that means that our point B has deflected downwards. Okay. We should just take note of that for now. Okay. So it has deflected downwards. These support conditions are critical to us when looking at the deflections, not only for the semester, but pretty much throughout the any structural analysis course, right? Understanding the support conditions with respect to both reactions and both deflections is critical to being able to properly analyze the structure. All right. So the basic supports are the pin, roller, fixed, and then the free end. So a side information, not too critical, but let me just put it here. This will be explained more next semester, but just so that we have an idea of what. Okay, so before the side information, so let me go over the supports. I'll use the pin support to explain. Some of you are asking that I go over it. Let me just go over it one more time. So support have reactions. That much we know, right? And then we know that for a pin support or a hinge support, it has two reactions. Okay. Reaction simply means preventing movement. All right. So if a pin support has a vertical reaction, it means that it prevents movement in that direction. Okay. A pin support also has horizontal reaction. It means that it prevents movement in that direction. A pin support has no reaction against rotational movement. All right. Again, as I mentioned, there are three types of movement that we focus on. The two translation, which is the vertical and horizontal, and then the rotation about a point. Okay, and that's how come you are able to get summation of forces in the y direction, then summation of forces in the x direction, and then summation of moment about a point. Right? These are some of the reasons why we come up with some of these equations, right? Okay. Yeah. So for a pin support, it has two reactions, which means that it will not deflect. It will not move up and down. It will not move left and right. Okay. So it means that for that support, no matter what load you apply, once it's within the elastic range, there's no way the support at A will deflect normally. Support at A will not deflect unless you induce or you impose some deflection on it. But typically, for now, supports at A will not deflect. Right? So there will not be any deflection of support at A, and that's how come that deflection delta A is given as 0. Okay. Now, when we take into consideration the rotation, all right, even though A does not deflect or does not displace, point A can rotate about its axis. And that's a mechanism behind why we are able to open and close doors, because about where the hinges, the door is able to rotate. So once it's rotating, it means that it's able to create an angle with respect to its initial position. Okay. So let's, so for example, if this is my, oops, wrong pen. So let's say this is my wall. Okay, I'm using this as an example. This is my wall, and I have my door here. So this is my door. So it's in plan, like it's like you are looking at it from the top. So this is the plan. So this is my door, and then I have my hinge right here. So this is my hinge in this red space. Okay. When someone opens the door or someone pushes against the door swings, right? So, oops. So initially, if it was in this position, it will swing to some position like this so that you can pass through, right? When this is happening, it simply means that your door is rotating. The door is rotating. That's all that is happening. It's rotating about the hinge right here. Okay. So this could be my point A in this case, and means that rotation here becomes theta A. Okay. All right. So with the site information, okay, I'll bring it up later so that I don't add too much information at this point. All right. So these are what we need to take into account. So let's look at an example, okay, of a proper case. So let's say I have a beam, okay, and then I have a load P applied on the beam. So this is A and B. So let me call the points where the load is applied C, okay, for now. Now, with time, this beam is going to deflect, something like this. All right. So once it deflects, we know or we have information that the displacement at A is 0. The rotation at A will not be 0. The displacement at B will be 0. Right now, we are focusing on vertical displacement. We can also have horizontal displacement, but then we mostly assume that beams, or we make the assumption that beams are rigid axially. And what that means is that the deformation in the horizontal directions are very small. So we can assume that they are 0. And that's how we are only looking at vertical displacement for now. I'll explain this a bit more later. Okay, and then here, theta B is equal to 0. Okay. Now, if we take point C used to be here. Now point C is somewhere here. So there'll be some deflection C. So at C, our deflection will not be 0 because of the fact that there's some deflection. Okay. If P is at, let me write with a neutral color. If B is at midpoint, okay, it's likely that the rotation at C will be zero. It's likely. Would explain why this is the case. It's likely, right? That the rotation at C could be zero. For now, let's not bother too much why that's the case. We'll come to that very soon. Um, Now let's look at another case where instead of a pin supports, we do have fixed support at the end. So pretty much the same length of beam with the same load right at mid-span, and its deflector shape will be slightly different. Okay, because at support A and B, the beams are fixed, or the supports are fixed. So if the supports are fixed, it means that the displacement at A is zero. The rotation at A will also be zero. Sorry, this is not equal to zero. Okay, sorry. The displacement at B is equal to zero. The rotation at B is also equal to zero. Okay. So again, if this is our point C right here, our point C will undergo some deflection. So the deflection at C will not be equal to zero. All right. So this is, let's say, case one. Let me call this case two. So it's the same structure, but different loading different support conditions. Okay. And later we'll come to understand that the displacement at C for case one let's say case I, is greater than the displacement at C for case two. Okay, we'll later come and explain why this is a concept, or what yeah. And this governs the reason why sometimes when you are designing a structure, you prefer to go in with fixed supports than pin supports. Um, Let me just put the side information over here. So when drawing the deflector shape, when drawing the deflected shape or the elastic curve, as we have two options, just looking at the general position of the load. Okay. Or we can also use the bending moment. So the bending moment diagram to draw the elastic curve. Okay. So for example, in this case one and case two that we are looking at, it's easy to just look at the direction of the load. It's acting downwards. So definitely the deflection will also be downwards, right? So this is just the general position of the load. But sometimes when the loads become a bit or when the loading is a bit more complex, maybe there are about 2, 3 different types of loads, and some are going up, some are coming down, then it becomes a bit difficult to draw the to just straight away be able to draw the elastic curve. Okay, so let's look at a quick example of that, and then you can move on to something else. So let's say I have this simply supported beam. And I have these loads acting on them. So let me just create that some is going up, some is coming down. All right. So let me call this B1, call this B2, so A, B, C, and D. All right. So here I can so here I can draw the bending moment diagram. All right. With the bending moment diagram, I know you guys can someone tell me your bending moment diagram when you guys are drawing, is the positive side downwards or upwards? Can someone answer that for me? I think last week when I solved it in class, I used, which one did I go with? I made a positive upwards. Is that what you guys use? Or you go with um, a different, can somebody please answer that for me? Like for example, so let me explain maybe in case you don't understand what the question is. If I have this as my beam, all right. If this is P, my the bending diagram can take this shape. Okay. Where this is PL over 4. This is positive, or some books will do it this way. Okay, so this positive PL over 4. It's the same thing, but which one do you guys usually go with? Let me see. Positive upwards. Okay, all right. Fine, all right. Positive upwards is fine, so that should be this one. But you go through some books and they also prefer this approach. And the reason we prefer where the positive is down approach is because that that follows the direction of the deflected shape. Okay. So positive being downwards, it just follows the direction of the deflected shape. Okay. So it means that in this case, because if you're looking at the deflected shape, this is how the deflected shape looks like in for this particular beam. So it's deflecting downwards, right? So it's the reason you'll find that some books will go with this approach because they both are in the same direction. Yeah, so that's what really happens. But that's fine. This the one on the right also works, so it's good. Okay. So here, if I draw my bending moment diagram, so I have two options to do the bending moment diagram. Um, the diagram will look like, I'm just going to just draw um, a qualitative form of the bending moment diagram, not the actual value. So this are bending moment diagram. Okay, there's a bunch of straight lines. Okay, so here will be negative and here will be positive. Okay, so that's basically what you guys are used to. Or if I'm to go with what some other books do, okay, it's the same thing, please. So don't be confused about it. I'm just redrawing the same thing. Some books will go like, okay, so this is, so here's positive and this is negative. Some books will just flip it and go like, this is negative, this is positive. It doesn't change anything really. So you end up with your diagram looking like this. Okay, so this is negative, this is positive. It's the same thing. It's just that we have just flipped the position. Okay. And then positive is what sagging, negative is hugging, that kind of stuff. Okay. So if you look at it, this is how the deflector shape would be. Let me just draw it over. So this is the deflector shape. Okay. And I was able to draw that using this information over here. All right. Because definitely P2 will push the beam upwards and then P1 will push it downwards. So if I'm able to come up with a Bennett diagram, that should assist me in deciding how my curve would look like. At some point over here, this is 0. All right. So here, the moment is 0, as we can see. All right. Or the deflection is 0. And at that point, we call that point the point of, or the inflection point. So the inflection point. And this is where the moment is 0. Okay, so just take note of that. So this is the inflection point, the point whereby there isn't any deflection occurring at that particular point. Let's see if I can finish this today. Let me see. So let's look at the elastic beam theory. Okay, and that's basically the Bernoulli the Bernoulli oops. So the Bernoulli-Euler beam theory. And I think it was developed in 1750. Yeah. And it's still in use today. All right. And it gives a good, what's the name? A good approximation for the design of beams. There are other theorems out there. One of the most common ones is the Timoshenko beam theory, which is a bit more complex and a bit more accurate than the Euler, the Bernoulli-Euler theorem. But then the Bernoulli-Euler theorem is much more simple. And again, in design, we are dealing a lot with probability. All right. So there isn't the need to be 100% precise. As long as you are within a range of acceptable probability, then your design should be considered safe. All right. You'll spend a bit more time on this in strength of materials. Once you start looking at the stresses in beams, you would spend a bit more time on these beam theorems. So you go through it. I just take you guys through just the basic aspect of it for the purpose of this course to understand this course, but then you delve deeply into it maybe when dealing with strength of materials. So this was developed in 1750, and it has some assumptions. We'll look at what assumptions are, and I'll explain them shortly. It says that plane sections remain plane. Okay, and then um, deformed beam slopes are very small or are small. Okay, we don't want to go by too many um, adjectives, so they are small. So these are the assumptions that we make with respect to the beam theorem. I would explain shortly. So let's say I have a beam. Okay. So let me just draw some lines through the beam. Okay. Too many lines. Let me just take some off. Okay. Now let's say that this same beam deforms. So there'll be some deformation of the beam, doesn't look too deformed. Let me exaggerate the deformation. Okay. So when a beam deforms, there's a certain part of the beam which we call the neutral axis. Oops, different color. The neutral axis where there's no change during deformation. Okay. So let's say this same neutral axis is somewhere here. I'm assuming it's also like this. Oops, too many. Okay. So these red lines are still going to be there. They also deform along with the way the beam is. So what we mean by the plane sections remaining plane in a sense that these lines are what you call the plane lines. I mean, I just lines drawn so that you can cut the section at any point. Okay. So these same lines are the ones here. And what happens is that if so this is the undeformed, and this is the deformed. So with the undeformed, these vertical lines make an angle of 90 degrees with a neutral axis. Okay. Now, when they undergo deformation, normally they will not make an angle of 90 degrees with the neutral axis. I mean, these lines, all right, because they have been shaped into different directions. But with respect to Bernoulli, he's assuming that, you know what, regardless of what happens, at every point, the beam should make an angle of 90 degrees with respect to the neutral axis. Okay. So that then the neutral axis does not change. It doesn't contract, it doesn't expand. Okay. So that's what he means by plane sections remain plane, regardless of whether there's deformation or not. Okay. And again, when it deforms, the angles are very small. Okay. Let's look at it this way. Let me exaggerate. Can I draw the shape? Okay. So let's look at this beam. It has these supports. Okay. Now let me take a section of the beam. So this section right here. Okay. So here's A, B, C, and D. Okay. And it is the entire length of the beam, L. So in this state, the beam is undeformed. All right. Then we have the neutral axis, just so that things look a bit correct. Let me just. So this is a neutral axis. That the neutral axis simply means that it is a position along which, when your beam deforms, that part of the beam doesn't have any change, or there's no change in the length of the beam during deformation. Okay. Things will come full circle very soon. Again, if at some point you don't get anything, you can just let me know. All right. So this is the undeformed shape. Now, so let's draw a simple version of it. Right. So this is a simple version of the beam. Let's say we apply a load here, P. So a load P is applied, which means that it will deflect upwards. I mean, just to explain the concept of the elastic beam theory to us. So once it's deformed upwards, we do have, so now this is our new shape. Let me try and see if I can exaggerate the shape a little bit more. So this is fine. So now this is what we have. So now our A, this might interfere. Let me just move this guy here away from the spot up here a little bit. Okay. So now our A has become A prime. Our B has become B prime. Our C has become C prime. And then our D is now D prime. So let's say that the distance here between C and D is the X. All right, so CD is equal to AB is equal to dx. Okay. Now, once let me draw it better here. Okay, so that I just exaggerate. Okay, great. So we can see that once the beam deforms, AB, or let's say A prime B prime is greater than AB. Okay. Then C prime D prime is less than CD. Okay. So if you have a beam or any thick material and you bend it upwards, what happens is that the portion close to the top would elongate and the portion close to the bottom will contract. All right. So this zone here is undergoing contraction. Okay. And then the zone up here is undergoing elongation. So if some part up is going is undergoing elongation and some part is undergoing contraction, then it means that somewhere in between there will not be any change. No change. Okay. So it's like moving from negative to positive. It means that at some point there should be zero. Okay. So the point that we have zero change or no change. That point becomes your neutral axis. Okay. And as the beam deforms, you can actually what's what I'm looking for? You can pretty much extend the deformation whereby it's as though it's trying to form a circle. So that circle would have a radius or a center point. All right. And then from the center point to your neutral axis, this will become the radius of the supposed what's the name? Of that curve that is likely going to complete a circle. All right. So that curve or that curvature, so then R here is usually called the radius of curvature. Okay. So now let's try and make some meaning out of it. So let's take the A prime, B prime, C prime, D prime portion and then make some meaning out of it. So I'm just going to draw that over here. Oops. Okay, so let's, and again, the angle, this angle here, maybe it's better if I draw it over here rather. The angles are very, very small. Okay, so just take a note of it. So this angle here, theta, is very small. Okay, so let me call this small portion the theta. This distance here is the x prime, and then the one below will be the x prime 2. Okay, so that or the x prime prime. So here we have the x prime prime. So I can just bring it here. This is the x prime, and then here the x prime prime. Then somewhere in between, we have the x where there's no change. Okay, so simply put, it means that the x prime is greater than the x, which is also in turn greater than the x prime prime. Okay, because there's expansion at the top and then there's contraction at the bottom. So let's just take a note, or elongation. Okay. So this is your center. So this point is your center. Nothing has changed. So from the center to the neutral axis, that distance here is going to be our radius r. Okay. So using the Pythagoras theorem or the right angle triangle theorem, I can just rewrite this in a much more simple way. So this is your d theta, this is your dx, and this is your r. Okay, or maybe, so let me expand a little bit so that it includes everything. So this is your dx, sorry, different color. So this is your dx, and this is your dx prime. But our focus is up to where it's between this and that. Okay, we'll come back to the dx because we don't know what this is, so we can represent this value by y, where y can vary. Okay, so in this case, it means that using the right angle theorem, I have my opposite, I have my what's the name? Adjacent. So it means that the angle tan d theta is equal to the x over r. Okay. But then for small angles, tan d theta is approximately the same as d theta. Okay. So tan d theta is almost the same as d theta. For very small angles, the change is pretty much not or it's negligible. Okay. So which means that I can rewrite this equation as d theta is equal to dx over r. And then that implies that the theta over the x is equal to 1 over r. Am I correct? Yeah. And this is what we call the curvature. Okay. And we define the curvature as so it's a measure of how much bending deformation a beam has at a particular location. Okay, so how much a beam can bend, right? So it means that the more the curvature, the more the beam can bend. All right. And anytime a beam bends, deformation is pretty much occurring at that particular point. Okay. Now, I can also rewrite the theta in this form, that the theta is equal to, if I'm to use the principle of similar triangles, then it means that my my opposite is dx prime, and then my adjacent is r plus y. Right, they both are the same, regardless of what we look at. Okay. So here I can compare the two. So let me say that this is my equation 1. That's my equation 2. So if I compare 1 and 2, we should end up with so we can say the x over r is equal to the x prime over r plus y. Okay. It's just something for us to appreciate what goes on. So here I want to make the x prime the subject. Okay. So that would imply that my dx prime will be equal to dx over r into brackets r plus y. Okay, which when expanded is the same as dx plus dx y over r. Okay. We'll come back to this. So let me call this equation 3. Come back to equation 3. Can someone please answer me? Have you guys started doing axial strain or normal strain in strength of materials? I'm sure you've met at least once. What have you guys done so far in strength of materials, please? If someone can answer me. You haven't met, or you have met, and what did you guys study? You only type no, sir. It doesn't really help me as to what you want to see. Okay, so let me just go ahead and then explain that. So So this other side, I was hoping you guys have already done that, so I don't need to, but let me just explain. So let's say I have a bar. Okay, maybe this is my bar with a support at the end, and apply a load P to this bar. Let me just make it shorter. Let's say I apply this a load to this bar, an axial load. All right. P, with time, the P will force the bar to elongate. All right. So it means that if this was its initial length, L naught, with time, the bar would extend all the way to somewhere here. So now it means that because of the load, your bar now has a new length, L1. So there's been some additional length added to the bar because the bar is elongating. It's just like how we have the rubber band, right? Typical rubber band where you can stretch it, right? Because you are applying some load to it, so you can stretch the rubber band. In the same way, also, you can also stretch if you apply a load P to the structure or to maybe an axial member of this nature, it would elongate, all right? So there'll be some extension E, and this E is simply the difference between the initial length and then the new length. Okay. So we call something axial strain. So how much deformation has occurred, all right? So the axial strain is simply the change in length. Okay. So the change in length divided by the original length. Okay. So this will become the change in length L1 minus L naught over L naught, or in simple terms, E over L naught. Okay. And the axial strain, let me just rewrite that over here because I need to show you the sign, the symbol, sorry. So the symbol for axial strain is epsilon. Okay, so if you hear the word epsilon, then that is the axial strain. All right. Why am I going through all of this? Just to explain one concept to us. So I can come back into the space. All right. If this is my original length, the X, okay, so the X is my original length before the beam deformed, and then the X prime is my new length in this case, then I can use that concept to find the axial strain. Okay. So using the same idea, it means that my axial strain, so this is just an aside, just for us to, you guys will do this a bit deeper into strength of materials. So you should be fine. I'm sure by the time you finish going through this strength of materials. So here, my axial strain epsilon, oops, this looks funny. It is a difficult symbol to usually write. So it's equal to the X prime minus the X over the X. All right. So the new length minus the original length over the old length. Pretty much that's what it means. Okay. So I can call this equation 4, even though I don't need that, but let me call this equation 4. And I'll say put 3 into 4. So that will give me wherever I see my epsilon, my dx prime is what? Dx plus dx y over r minus dx all over dx. Right, so this is what we have. The equation will reduce to dx y over r divided by dx, which is the same as y over r. Okay. My y is a bit funny. Okay, so I think this is better in terms of writing the y. But the strain has a relationship, or when there's bending, the strain has some relations between the radius and then the what's the name? A varying distance called y. Okay. So if you go back to our initial object, all right. So these are the x prime prime. These are the x prime. Now we have at the center the x. All right. So what it simply means that I have y here. Okay, at least from what we have over there, right there. So here's y. Okay. But this y varies. Okay. Y varies. So we can have y. So y varies from the center to the outermost fiber. All right. So y can vary. It could be 0 at this point, and it could be highest up there. Okay. We can also have y vary downwards. All right, but then that'll be negative. Okay. That's the idea. So upwards, this will be positive. Downwards, this will be negative. Okay. This is just to help us to understand what strain is all about. You do it a bit deeper going in the strength of materials. Right. But this has to do with bending strain, or well, in a way to, yeah, bending strain. So it means that y if y is somewhere here, if here is y1, then y1, so it means that the strain at this point, strain 1, there'll be a strain here called sigma 1, sorry, epsilon 1. So that strain at 1 is simply y1 over r. Okay, the r is just a radius, so that will not change. If I want to find a strain at another location, let's say y2, then it means that the strain at that point will be equal to y2 over r. All right. Which means that the maximum strain would occur when y is maximum. So it means that maximum strain epsilon max is equal to y max over y. Okay, so strains are lowest at the neutral axis, and then they are highest either at the upper outermost fiber or the lower outermost fiber. One of them will give you the highest, what's the name? Strain. Okay. So you delve deeper into this. Now, when beams undergo bending, stresses are developed. Okay, are developed in the beam when there is bending. Um, add this to second note it. Can I update it? Let me see if I can do something shortly. Maybe this will help us appreciate what is happening. Hopefully this appears. I'm trying to load something for us to have a look at quickly. But thank you. Okay. So if you go to vCampus, I have what's the name? I have a whole text over there on this elastic beam theorem thing so that we can better appreciate what is happening. So it gives the introduction of the theorem, what it goes into it and all of that. And then it looks at the bar before and after the formation. So pretty much everything I'm discussing here can be found in the notes. All right. So I think maybe this one looks a clearer. It's the same thing. So this is your general equation for finding the delta called dx over r, and then this is the strain which I just showed you guys, and that will be the strain as you move. So y would vary from 0 at the x and then highest upwards. So this becomes the strain behavior. Okay. Then also when you have, yeah. So anytime there's bending, that will also develop some bit of stresses in the beam. And to find the stress in the beam at any point, this is the equation for finding bending stress. Okay. So the bending stress sigma is equal to the my over I, where m is the bending moment at that point in the section. Okay. And then the y is the distance from the neutral axis to any point along the cross section. Okay. What we are looking at, if this is your beam, you've cut through it and you're looking at a cross section. So your y is pretty much somewhere here. So this is your y. Okay. And you're looking at the stress behavior along that particular cross section. Okay. So sigma is equal to my over I, where I is the moment of inertia. Okay. You look at them, look at some of these things in the materials, right? So this is the bending stress equation for a beam, which is what's the name? Undergoing some bit of bending. All right. So taking us, let me go back to where I was. All right, so stresses are developed in the beam when there is bending, and these stresses, sigma is equal to my over I. You could just read through the notes on the vCampus, and then if there's something that it's a bit difficult to understand, I can explain to you guys later. So the parameters are there, the sigma, it has this funny shape like that. Okay. So this is sigma. Okay. So that's how we call the bending stress. Then we have m, bending moments. Y is the distance of a fiber under consideration. And then the um, what's the name? The oops. The so my over I is a sigma, and then my screen is messing up. A second. Okay. So let me call this equation 5. And then per Hooke's law, we are looking at what's the name? Elastic region. So from the Hooke's law, it says that sigma is equal to E epsilon, where E is the Young's modulus. Okay, so this is from the Hooke's law. So if E is Young's modulus, I have my sigma, I have my epsilon. I can write an equation in terms of that. So um this should mean that my sigma is equal to E into bracket Y over R. Epsilon is Y over R. This is my epsilon, Y over R, where epsilon is the axial strain. All right. So my stress, I know it to be My over I. Okay, so from here, I can do a bit of movement and then come up with some useful equations for us. Okay. So here, the Y will cancel out, which means I have M over I equal to Y over R. Okay. Oh, sorry. It's equal to E over R, which means that 1 over R is equal to M over EI. Okay. And this 1 over R, which is equal to M over EI, we have already defined that somewhere up there. We mentioned that here, the theta dx, or the theta over dx is equal to 1 over R. So I can come back here and go like, okay, oops. Then this is equal to the theta over dx. All right. So if this is the theta over the x, then I can rewrite this equation here that, okay, the theta is equal to M over EI dx. Okay. This is a very important equation for us. Okay. And this is used to find the slope and find deflections in um, any of the sub disciplines we'll be looking at. So let's say we integrate both sides. If we integrate both sides, it means that we'll have, so integrate M over EI dx. It means that the theta then becomes M over EI dx. And this is the slope. Okay, or the rotations. So to find the slope, this becomes our equation for the slope. Okay. And you will come across this equation a number of times going forward. So let's just have that in notes, in mind. The proof or how to come about this equation is fairly straightforward. The only challenge is that because you guys have not done a bit of strains and stresses or in strength of material, so things seem a bit new to you guys, but isn't that it's not that difficult to understand. So the everything in this space here is right here to as well. Okay, the same idea is being applied. Okay, so the above information here is just to explain to us how the Bernoulli Euler beam theorem works. Okay, so I think the entire um, theorem we would again work around it. So in its simple terms, um, so this is its m. Oops. So let's say m is equal to ei d theta dx. This is in its simple terms, but usually we don't write the equation in this manner. We tend to do a bit more to it than just writing it in this format. Okay. So let's look at completing the Bernoulli Euler equation. And with that, we'll need the double integration method in this case. Okay. So let me exaggerate the section that we had earlier. I think let me just redraw it somewhere here. All right. So we had something like this. Okay. Here was our d theta, and this is our r. Okay. And then let me call this the x just for to help us to arrive at some value. Let me call this ds. And let me call the horizontal distance of that the x and the vertical distance dy. Okay. Um, let me put a small angle over here. Oops. Okay, let me just make this one theta. It doesn't really change much. And just to explain the concept. Initially, what we had here, what we were looking at in the with respect to all of these diagrams and all of that, even with the one I drew earlier, where's that shape? All of these shapes that we are looking at, we're assuming that the going back, we're assuming that the y was 0. That if the y is 0, then it means that your dx is the same as ds. It doesn't change anything. All right, so it's the same as what we had earlier. It's just so that to expand the equations, I need to show you guys actually generally what happens in case the rotation is not vertical as or horizontal as we had it earlier, and whereby there's a bit of skewness to it, and it means that there will be a dy component. Okay. So to find ds is simply equal to square root of the y squared plus the x squared. This is the Pythagoras theorem. Um, So that could be written somewhere. So this is your dy, this is your dx, this is your theta. All right, so it means that theta is simply what? Again, these are very small angles, so tan theta will be the same as theta. So dy dx. Okay. We have already established that 1 over r is the same as the theta. So in this case, it would be the s. That when the s approaches, or where the y approaches 0, then the s is the same as, also approaches the x. Okay, so pretty much the same thing written here. Okay. So in that case, I can going back to our previous calculations, then it means that 1 over r is the same as the theta dx, right? And then we know that theta in itself is dy dx. Okay, so then this gives us d dx to bracket dy dx. So this should give us the squared y dx squared. And again, 1 over r is equal to m over ei. Okay. So this is the same as the squared y and then the x squared. So that's like double differentiation. All right. So here, if I'm to make the moment the subject, then m then becomes me, oh sorry, ei, the squared y over the x squared. Okay. So this equation here is what we'll call the Bernoulli Euler equation. Or some will say the elastic equation for bending. Okay. So what and this is a second order differential and differentiation. So let me just put it here. Second order differential equation. So what's all this about? What this means is that if you have a beam, you apply some load to it, right? This shape, this elastic curve, right? This shape can be drawn using some form of the bending equation. Okay. So let's say we integrate this equation once. So let's start with some key information. So let's say integrate equation above. Okay. So ei, the squared y over the x squared is equal to m. All right, so let's integrate both sides. Oops. So if you integrate both sides, then it means that we'll end up with ei dy dx is equal to m dx. Okay. Or m dx plus, assuming there's anytime you do integration with unknowns, there's always a constant. So m dx plus a constant a. And you'd realize that this is the same as the slope that we found earlier, where our slope was dy dx being equal to integral of what's m over ei. Okay, so this is theta. If you go up here, I think somewhere, yeah. So right in the space over here, where theta is equal to integral of m over ei dx, and then it's the same as what I have over here. Okay, so theta is equal to m over ei dx. Okay. Oops. So this is the slope. So now if we are to integrate again, so let's say integrate twice. So integrate the original equation twice. It means that the same as integrating the, so let me put this, this is maybe equation, I think 7. This is equation 8. So integrate twice, which is the equation 7, should be integrated twice. That would give us, so it's double integration. We should end up with ei squared y over the x squared, which will be equal to m dx. So double integration. If you double integrate a differential, which is already a double differential or a second order differential, then it means that you end up with what? A y, or should I say a deformation. So eiy then becomes, if you were to double integrate m dx, that will give you a constant a, which then will be integrated to give you ax plus another constant b. Okay. So this equation here gives us the deflection. So this deflection or this displacement is what we call the double integration method, because we integrate the Bernoulli equation twice to give us the what was the name? To give us the deformation. Okay. So let's have this in mind. We'll come back to it. Now, instead of integrating, let's differentiate. Okay. So let's differentiate equation 7 once. Okay. So if we differentiate equation 7, then it becomes ei the cube y over the x cube. And this is equal to the m dx. And the m dx will give us what? The shear force. Okay. Then again, if you are to differentiate equation 7 twice, then it means that we have ei and the 4y over the x4, which is the squared m over the x squared. And that is assuming that, let's say, the shear force is F in this case, then it means that this is the same as the F dx, and the F dx will give us the load intensity. Okay. So for a UDL, this will be how to find a UDL, the load intensity, and then differentiating once was what we need to find our what's the name? To find our shear force. And then once you integrate once, you get a slope. If you integrate twice, we get the what's the name? We get the deflection. All right. So one of the most common equation you find yourself coming across are these two. Okay. you are already aware of the shear force equation um, from your um, basic structures class. And then there's also an additional one for us to look at today, which is the loading intensity, which again is complements to the shear force equation from the basic structures class. So we have, I think, time to try one example. Let's look at how all of these things come together, right? From all this time, we just been looking at derivations and solving, just dealing with variables and all of that. So let's see how everything comes full circle. So let's say we have a beam. And the beam has a UDL, a uniformly distributed load on it. Okay. Let's call that W, which is in kilonewtons per meter. We don't know what that value is. This is our length L. This is A, and that is B. Okay. The deflector shape would be something like this. Let me just draw it on the side. So this would be the deflector shape. Okay. So let's look for a point at the midpoint C, and then we want to find the deflection at C. So we want to find delta C. So that's the general idea. So find delta C, or maybe in this case, YC is the same as delta C anyway. So let's find this deflection. And to do that, we need to formulate an equation for the moment. Okay. We know that M is, or we have information that what M is equal to EI, the squared Y, divided by the X squared. So M is equal, let me just put that over here, EI. Please, the E is the Young's modulus, and then the I is the moments of inertia. Okay. And together, we call them the flexural rigidity. So now we need to formulate an equation for the moment in terms of X. Okay. So let's say X starts from A towards B. Okay. From here, we can easily find our reactions, VA and VB. Okay. VA is equal to VB, which is equal to WL over 2. Okay. You just have to find the total load of the UDL, which will be W times L, and then you divide that by 2, and that should give you the load for each, or that should give you the reaction for each of the supports, the vertical reaction. So to find the moment at any point X, so MX or M is simply VA times X minus WX squared over 2. I think we went through this last semester. Sorry, last week, So VA minus X. So this is your equation for the moment. You can simplify it. VA is WL over 2. So it becomes WLX over 2 minus WX squared over 2. Okay. So what this means is that if I want to find the deflection at C, which in this case will be our maximum deflection because of the way the load is, means that we have to integrate mx twice, okay, to get our deflection. So in the first case, we can start with our first integration. So with the first integration, so it becomes EI dy dx will be equal to WLX over 2 minus w x squared over 2 dx. Okay, so here, if we integrate this, let's see what the integration will be. Okay, let me simplify so I don't need to go through. So here I can bring w over 2 out, and I'll have lx minus x squared, because w will be a constant. The only variable will be changing, which with respect to x is x. So I can come in here and then rewrite this in a nicer way. Oops. So w over 2 lx minus x squared dx. Okay. So this will give us w over 2 lx squared over 2 minus x cubed over 3. I'm to assume we can all do integration. All right. And since we don't have the limit to integration, we need to include a constant. All right. So now we can do our next integration. So this is the first one. Now let's do the second integration. Okay. So with the second, we come back and just integrate the first one. I mean, the first integration again, that's all. Right. So EI y will be integrating w over 2 lx squared over 2 minus x cubed over 3 plus 8, which is a constant. So this will give us, again, w over 2 lx cubed over 2 times 3 is 6 minus s cubed over, sorry, x exponent 4. And then, so 4, 3, 12, right? Yeah. And then if you integrate a constant, it becomes that constant times x plus a new constant b. Right. So here, this space here is equation, or the general equation for the deflection for this particular beam. Okay. So here we have these constants a and b, and we need to know what these constants are. All right. So to determine the constant, we need the boundary conditions. So the boundary conditions will be, some of them, not all of them. Some of them will be what we discussed earlier, which has to do with all the way up there when we're looking at the different support. So these support conditions will play a role for us when it comes to looking at the boundary conditions. Okay. We'll also add a few to them, but for now, this should help us to solve our example. Okay, so we need the boundary conditions. I think when you were dealing with arches and basic structures, when you were formulating the equations for, I think, a 3-pin arch, you had to understand what boundary conditions were to find what some of the constants, if I remember, or if I think that's what you guys did, then you should have done something similar to what we are about to do. Okay. So we need to find A and then find B, or find a constant A and B. Okay. So so let me do something. Okay, let me change it from A and B. So let me call this one C1. Okay, so that it doesn't conflict with the support A and B. All right, the support A and B are not the same as the constant A and B. So I'm just changing that to C1 and C2 so that it doesn't create confusion. So at support A, x starts from A towards B. So x is 0. So that's this starts 0. And then your y is 0. Y here is the deflection. If you come at A over here, your delta at A is 0. So the Y at A is 0 because there's no deflection at the support A. A pin support cannot deflect. So at A, X is 0, Y is 0. This here indicates deflection at support A. Okay. So if A is 0, Y is 0, I can put this information here into my deflection equation. Okay. So if I put into my deflection equation, it means that C2 will be equal to 0. Okay. So Y is 0 at this point. So this is Y. Y here is 0. Oops. So Y is 0. So this, the equal to sign on the left goes to 0. X is 0. So this whole place goes to 0. This is 0. So that is 0. This is also 0. So it makes C2 0 or 0. Okay. So it means that our equation then would reduce to EIY being equal to W over 2 LX cube over 6, oops, minus X4 over 12 plus C1X. So we have information on so we know what our C2 0. Now let's find C1. So to find C1, you can look at point B. At B, again, X is 0. Sorry, X is not 0. At point B, X is equal to the entire length of the beam, L. But again, our deflection at that point is 0 because it's a roller support, and per the boundary conditions, there can't be any deformation at that particular point. So if you are to sub that into the deflection, the new deflection equation, it means that I'll have 0 is equal to W over 2. This will be L4 over 6 minus L4 over 12 plus C1 times L. So here we can make C1 the subject. And if we do that, so here 0 is equal to, let me just simplify this. We get WL4 over 24 plus C1L. Okay. So here it simply means that our C1 will be equal to minus WL cube over 24. So now I know what my C1 is. I already have my C2 being equal to 0 somewhere here. So once I have these two, it simply means that I can now write my equation properly, whereby EIY is equal to W over 2 LX cube over 6 minus X4 over 12 minus WL cube over 24X. So I'm replacing the C1 by minus WL cube over 24. All right. So now this becomes an equation with which I can use to find the deflection at any point along the beam. All right. So what this simply means is that this equation defines this curve. So the curve, as we see it here, how this curve is drawn is done by using the equation over here. So that's this is not so this is more or less an equation with the highest x what being 4. So it's not parabolic, it's not cubic. It is what's the name? How will you call it? An equation whereby the highest exponent of x is 4. I don't know why there's a name like that for it. Maybe um, quad something, some way. So what it simply means is that um, if this is your beam, okay, when x changes from 0, so when x changes from 0 to L, when x is 0, if you put x into this equation, you get a value for y. If x is 1, you get a value for y. So you get values for y at different locations of x. And these points, when joined together, is what gives us the curve as we have it. All right. So this curve is drawn using the above equation. Okay. So we need to find the deflection at C. Okay, so C here, where C is at the midpoint. So C is at the midpoint, which means that at the midpoint, your x is equal to L over 2. So at C, your x is L over 2. So if x is L over 2, I can put that into the equation above and then find the corresponding displacement or deflection y. So EIY, let me call this one YC because I'm finding the deflection as C. So this will be equal to W over 2 into brackets. Wherever I see X, I put in L over 2. That's pretty much what it is. So this one becomes L4 over 48 minus L4 over 192. Then here to minus W L4 over 48. Okay. So these are, once you substitute X with L over 2, these are the set of equations that you have. Okay. So EIYC would be equal to, you get minus 5WL4 over 384. Okay. So the EY can go and divide, which means that your YC is minus 5WL4 over 384 EI. So here we have the deflection at C due to this UDL acting on a simply supported beam. Okay. The negative here, the negative in front of the equation here just indicates that we are looking at a downward. So this is for a downward deflection. Okay. So normally what happens is that you find this deflection caused by the load. Then when you get this deflection, which in this case will be your maximum deflection, then you compare it with what the code stipulates. Right. So your maximum deflection should not exceed what the code has. So let's see. Just to make meaning out of all that we've been doing. Let's say we have a beam 4 kilonewtons per meter. The length of the beam is 10 meters. This is A, this is B. If I want to find the deflection at C, which is the maximum deflection, then I can easily put that into this equation whereby YC is equal to 5 times 4 times 10 exponent 4 divided by 384 EI. So let me put an equal to sign here and put a negative over there. So this should give us minus 521 over EI. Okay. So the above equation, the YC equals 5W4 over 384 EI only works for a simply supported beam with a UDL on the entire length of the beam. If the support conditions change, if the load position or the load type also changes, your equation would also change. Okay. If you have to look at this, we should be ending after this example. If you have to look at this from first principle, as I did earlier, we can find our VA and we can find our VB. Okay. I'll leave that for us to look at it. So our VA will be 20 kilonewtons, and our VB also be 20 kilonewtons. Just a quick one. If for some reason you are struggling or you're having challenges with how to find reactions and how to draw shear force and bending moment diagrams for typical basic structures related questions, please see the TAs, or you can see me. We arrange a time and then we can help ourselves. All right, because everything we are doing here requires you to understand how to find reactions, how to find bending moment diagrams, especially. So if V and VB are these values, then the equation for the moment mx is 20 times x minus 4x squared over 2. So that should give us 20x minus 2x squared. All right. So I can integrate this twice. So let me do the first integration. Dy dx, 20x minus 2x squared dx. So this will give us 20x squared over 2 minus 2x cubed over 3 plus C1, which we don't know what that is. Then, so this is the first integration. And for the second integration, that is EIY, will be equal to, so 20 x squared over 2 minus 2x cubed over 3 plus C1, all of this dx. So this will give us 20x cubed over 6 minus 2x4 over 12 plus C1x plus C2. Okay. So this from first principle. So at A, where x is 0 and y is 0, it means that our C2 will be equal to 0. Okay. Then at B, where x is equal to 10 meters, our y is still 0. So we should end up with a C1 being equal to, I think, minus 500 over 3. If you do the math properly, that's what you should have. So with knowing C1 and knowing C2, we can put those two into this equation here and then write the proper general equation for the structure. So it means that EIY will be equal to, so this is 10x cubed over 3 minus x4 over 6 minus 500 by 3x. So here's your equation for finding the deflection along the entire length of the beam. Okay. So for C, our x is equal to what? L over 2, which is 5 meters. So to find the deflection at C, so it becomes 10 times 5 cubed over 3 minus 5 exponent 4 over 6 minus 500 over 3 times 5. And this should give us minus 521. All right, so it means that my YC will be equal to minus 521 over EI. So this answer here is the same as what we had from just putting the values into the previous equation. So with the double integration method, we can look at it in this way. It is a pretty cumbersome equation method, in the sense that you need to know a few things. One, how to integrate. That is critical to everything when a double integration method works. And as the name implies, you have to integrate twice, which means that you have at least two constants to deal with, two unknown constants to deal with. So in oops. So what we need is to first formulate moment equations. Yeah. And it's something I would strongly advise you guys to master that aspect of structural analysis, how to write moment equations. And these are normally written in terms of the direction x. This is so critical to a lot of the things we do and then we will do later. How to, whereby moments are written in equation form. All right. So what you were used in the first year, where you just look at moments at critical points and then draw your Bendel diagram, that might not suffice for certain aspect of the structural analysis course. Okay, so I'll advise that we build our skill sets on how to formulate moment equations. Okay. Then when you formulate the equations, we need to know how to do integration. Okay, in this case, we are looking at double integration. Okay. Then also find constants. So find unknown constants. And this will require us to understand boundary conditions. So understand and then apply boundary conditions. Okay. So just the last bits, and then so this is what we need when we are looking at the double integration method. Okay, so this is for the double integration method. So normally the double integration method is useful for finding the deflections. All right, not yes, you can also find slopes anyways, but the whole idea of the double integration method is to find deflections. All right. If we were to find, let's say we were to find a slope, so let me just go up, up, up. If we were to find the slope, maybe the slope at A. So if we were to find, let's say, slope at A, which would not be 0, Then for the slope at A, we only need the first integration. All right, so the first integration here in this space. All right, so once we find C1 where C1 is 0, then it means that our slope, so this just on the side, just for us, so that our slope EI dy dx will be equal to W over 2 Lx squared over 2 minus S cubed over 3. So that if at x is equal to 0, where we want to find the slope theta A, am I correct? Let me see if I've not missed anything else. Boundary condition, let's find C1. Okay, let me leave it as it is because I need to find the C1 in this case, which I haven't found yet. And to find the C1, and I need to find the y dx, right? Which is, we'll look at that next week so that I wouldn't have to rush through it. Okay. But there's a way to find the theta as well, whether theta A or theta B, one of them. Okay. But here, the boundary conditions to finding C1 will require me to know what x is and also to find the y dx, or at what point the y dx is 0. And typically that would be at midspan. So maybe if x is L over 2, then the y dx is 0. Then I can use those two to find C1. Okay, then if I find C1, then from there I can use that too. Once I find C1, I put C1 into this equation, then I can find theta A and then theta B. So we'll look at that next week. Any questions? Hey, what am I seeing here? How come I'm now seeing all these chats? Okay. It wasn't showing on the other one. Okay. Oh, it was sent to me directly. Okay, that's how I didn't see it. Okay, it's fine. Positive or opposite. Please can we say gravity is also a cause of deflection? Yes. So can you go at the inflection point? The line is also breaking. Sorry. Sir, please, I'm confused. No, sir. We are currently okay. All right. I think that for whatever reason the chats were not appearing, they all just came all at once. Yeah. I'll work on it so that next week we don't